Yesterday we focused on charged objects, objects that have an excess amount of electrons, and what the distribution of those excess electrons would look like in this charged object, in this conducting sphere or conducting plate or whatever shape it was that we were dealing with. Up on the board right now you see the solid conducting sphere. This is the marble, except the marble that's made out of steel, or the marble that's made out of copper, or something that's a conductor. And for whatever reason, this solid conducting sphere has some excess charge on it, a whole bunch of extra electrons. Maybe it's a million protons and 1,000,003 electrons. Maybe it's 1,000,000 protons and 2,000,000 electrons. It doesn't really matter. We've got extra electrons on it. When we're talking about this, the full analysis that we do today is based on the extra electrons. It's not based on the 1,000,000 electrons that balance out the number of protons. It's based on the electrons that are over and above the number of protons that we have. The diagram that you see up here, we got 3 extra electrons. And we're going to look at one of them. Okay, yesterday we looked at all 3. Today we're just going to look at the one as part of a review. Let's look at the first one. The first one experiences 2 forces as a result of the other 2 electrons. First force is down this way. Okay, it's repelled by this charge up here. And the second one is over here. It's repelled by this charge over here. So we got 2 forces acting on it. One force to the left, one force down and to the left. Where is this electron going to go as a result of those 2 forces? In other words, the net force acting on that one single charge as a result of the other 2 is pointing in which direction? Good, down and to the left. Now, this electron goes as far away from the other electrons as it can. It would like to, in a sense, it would like to just keep going right down here, but it can't. And why can't it? Why does it get to the surface and then stop at the surface? It's got somewhere to go. It could go into the air there, right? The air surrounding it. Why doesn't it go into the air? Because there's an insulator. Good. So it's kind of like a little club in here, right? These electrons all scattered throughout. They're getting along, moving around, having some fun, playing a game of soccer. And then they decide, you know what, we've had enough of each other. Okay, we played enough soccer. We've seen each other too much in this confined space. So let's get as far away from each other as we can get. So they start moving as far away as they can get. They go to the outer surface. And then they say, you know what, it's a big scary world out here, out there in the air. Let's not go that far. Okay, we want to get as far away from each other as we can get. So we're going to go to the outer surface of our sphere. We're going to be evenly spread out because that means we're as far away from each other as we can get. But we're not going to go any further because it's different out here. And we don't like it out here. This is an insulator out here. Evenly spaced, as far away from each other as they can get on the outer surface of the material. Well, next we took a look at the flat conducting plate. We focused on the middle charge there in this solid flat conducting plate. The middle charge experiences 2 forces. Again, if we have 3 excess electrons, it experiences 2 forces. One as a result of the one on the left-hand side, charge number 1. One as a result of charge number 3 on the right-hand side. One of them was bigger than the other. One force is bigger than the other because one charge was closer, the middle charge was closer to one of them than it was to the other. Now, as a result of that bigger force, it's going to be pushed that way, right? Pushed in the direction of the bigger force. Well, as that distance becomes bigger and bigger and bigger between those 2 charges, that force becomes smaller. Similarly, as this force becomes smaller, this force becomes bigger. At some point, those 2 forces are going to balance each other out. They're both going to be the same magnitude. And at that point, we're in that stage of static equilibrium, that state, I should say, of static equilibrium, where forces are balanced and charges are as far away from each other as they can be. What we find is that they are, once again, on the surface and once again, evenly distributed. So here's the rule that we've kind of just seen. When you have a uniform object, whether it's a sphere or whether it's a flat plate, doesn't matter, a uniform object like that, then the charges are going to go A, to the surface, and B, they're going to be evenly distributed on the surface or spread out as far as they can be from each other on the surface. That's in contrast to the third shape that we saw, which was the pointy thing. Okay, the lightning rod, the finger as you walk across the carpet and go to shock somebody. Here we find that the charges go to the surface the same as they did in the uniform shape. but they don't get evenly distributed on the surface like they did in the uniform sphere or the flat conducting plate. Rather, they get more concentrated at the tip. Right here, these two guys are closer together than these two guys. They're more concentrated at the tip than they are on flatter areas or more uniform areas of this irregularly shaped object. Let's take a look at this charge right here. It experiences a force outwards caused by this one. It experiences a force this way caused by this one. Now, we'll call this F1. We'll call this F2. F2 can be broken down into two components, an X component and a Y component. The Y component of F2 is what pushes it to the outer surface. So that's why it goes to the outside surface, as opposed to sticking around inside this irregular shaped conducting object. The X component tries to balance out F1. Right? The X component counters F1, but F1 is bigger. So that means this charge is going to go towards the tip as a result of F1, that force bringing it towards the tip being a little bit bigger. Now, at some point, F1 is going to decrease because the distance between this charge and this charge gets bigger. As this distance gets bigger, this force goes down, and at some point, it's going to balance out with the X component of F3. At that point, it's going to stop. It's in a point of static equilibrium. The forces are balanced. The charges are happy where they are now. They're not pushed more one way than they are the other way. They're stopped. And when they stop, this is what we see. The charge is more concentrated or closer together at the tip than on the flatter surfaces. Okay, again, yesterday we said that's the lightning rod. That's the finger as you walk across the carpet and go to touch somebody. Okay, that's why as you're standing out on a golf course in a lightning storm, you don't hold your metal golf club up in your hand, up into the air, inviting lightning to strike. Okay? It strikes concentrated areas. It strikes pointy things because pointy things have the ability to concentrate electrons more than flat things. What should you do, by the way, if you're in a lightning storm on a golf course? Don't hold your club up in the air, right? What should you do? What's the safest thing to do? Well, go inside if you can, sure. Yeah. No, stay away from the trees, man. Stay away from the trees. You know what happens to trees in lightning storms? They explode. You know why they explode? Because lightning generates so much heat that the water inside the tree will almost instantly boil and turn into steam and expand as it does that and literally make the tree explode. More people die from exploding trees in lightning storms than from direct lightning strikes, believe it or not. Don't stand by the tree. You might not get struck by lightning, but you're going to get killed by tree shrapnel instead. Make yourself as rounded as possible. In other words, you don't want to be standing up, with a pointy head for lightning to strike. Make yourself in a ball. As silly as it sounds, right? Everybody's running away from the lightning storm. You're the guy that's in the middle of the field all kind of huddled up in a ball. As silly as it sounds, that's safer than standing up or running across the field. If you can find a little valley to get into, kind of a little dip like this, get in there. How come? Yeah. Lightning's going to take the easiest path, right? The easier path than right there would be if you're rolled up in a ball right here. That would be an easier path. You're more likely to get struck by lightning than you are down here. But easier than that would be you standing up right there. A, because you're closer to the cloud, and B, because your head's a little more pointy than it is when you're kind of balled up like that. Ideally, get inside. If you can't do that, then make yourself as rounded as possible. All right, the last one we did was the hollow conducting object, which was saw yesterday, real similar to the solid conducting sphere. It's the same thing almost. In terms of the charge distribution, it's exactly the same. Charges all go to the outer surface. Hey, look, we've only got a surface. It's hollow, right? So we've only got a surface. Why do we say the charges go to the outer surface? Because there is an inner surface. The charges aren't there. The charges go to the outer surface, the outer part of it, and they're going to be evenly distributed again. Now, I want to take a look at the electric field for this one. Okay, the electric field points toward the negative charges. Well, inside this hollow conducting sphere, the electric field would point this way, and this way, and this way. Those electric fields cancel each other, giving us a net electric field inside of 0. Why is that important? Why is that important to have no electric field inside there? Well, for this particular object, it's probably not important. But if you're in your car or some other hollow conducting object that we call a Faraday cage, it means that the net electric field has to be 0 inside. It means that if you get struck by lightning, you're not going to be affected by that lightning. Because regardless, the net electric field inside is 0. Okay, somebody said, you're in a golf course, lightning storm, get in your golf cart. Well, if the golf cart is made out of metal, then yes, you should get in your golf cart. Usually the top part of it's not, though. Usually it's made out of plastic. Okay. If you're in a, doesn't matter if it's a perfect sphere, if you're in a hollow conducting object, the electric field is 0. And if the electric field is 0, you can't be affected. Just like the video we saw yesterday, right? Guy is literally being struck by lightning inside this car. He never even felt it. And the car was fine because it's all inside this hollow conducting object that we call a Faraday cage. Right? Let's move on to a little bit of new stuff here. Nothing crazy here today. Let's talk about electric potential energy. But before we do that, let's go back to physics 20 and talk about gravitational potential energy. We've done that a lot this unit, right? Talked about gravity so that we could understand electricity a little bit more. Gravitational force, gravitational field, and so on. Now it's gravitational potential energy. We define gravitational potential energy in physics 20 as the energy stored in an object due to its height. Now that's not a perfect definition. It was good for us in physics 20, but it's not perfect. We'll define it a little bit better in a couple minutes. But for now, let's go with that definition that you saw in physics 20. The energy stored in an object due to its height above a surface. The gravitational potential energy of this board marker right now, relative to this desk, is 0 because it has 0 height. The gravitational potential energy now is 20 joules as I lifted it up. My question for you is, how much work did I do to lift it from a potential energy of 0 to a potential energy of 20 joules? How much work did I do? I'll give you a hint. It's not a hard question. 20 joules, right? So the change in potential energy of this pen was equal to the work done on the pen, right? Well, the same thing applies with electricity. If we apply a force against a gravitational field, the change in the gravitational potential energy will be equal to the work done on that mass. Delta E is equal to W. But the work done in an electric field in moving a charge through an electric field, same idea as moving a mass through a gravitational field. The work done, once again, is equal to the change in potential energy. But this time, the change in potential energy isn't delta EP gravity, it's delta EP electrical. You have trouble visualizing moving a charge through an electric field? Then visualize moving a mass through a gravitational field. We can all see right now in our minds, whether you're looking or not up here, you can see the board marker being lifted through the gravitational field. Picture it that way. Even if it's an electrical problem, picture it as gravity. And then just make the translation to say, oh, it's not gravitational potential energy change, it's electric potential energy change. Now, I said a few minutes ago that we defined gravitational potential energy as the energy due to an object's height above the ground. And I said that wasn't a perfect definition in physics 20. It was a good definition, but it wasn't perfect. A better definition would have been the energy stored in a system of two masses a certain distance apart. So it's not the energy of the pen due to its height above the Earth. It's the energy stored in the system of the Earth and the pen a certain distance apart. Now, why is that a better definition? Well, because strictly speaking, it is the energy stored in the system of the pen and the earth. It's not the energy stored in the pen at all. It's the energy stored in the system of the earth and the pen. Why did we in physics 20 ignore the earth in this whole equation? Because it's so heavy. If I have this pen and the earth in the system, and I let the pen go and I let the earth go, which one's going to move, the earth or the pen? The pen, of course, right? We usually just drop the second part of the definition, the system of the pen and the earth, because the earth is so massive. We're talking about gravitational potential energy almost always in the context of the earth, and the earth is so massive that if I let the pen go, the earth isn't going anywhere. So it's, for all practical purposes, the energy in the pen. Technically, it's the energy in both, but for all intents and purposes, it's the energy of the pen because the difference in mass is so great. But when we're talking about electric potential energy, we can't make that simplification because the charges aren't usually as different as the masses are when we're talking about the earth and the pen. So we're going to define electric potential energy not as the energy stored in a charge due to its height above something, but rather the energy stored in the system of two charges, just like the system of two masses is the way we really should have defined gravitational potential energy. It's the energy stored in the system of two charges a certain distance apart. Again, a little more important to include both charges here because the charges are quite likely to be similar orders of magnitude, whereas the masses that we're dealing with, the pen and the earth, are dramatically different orders of magnitude. You're about to see what could be the easiest question in the history of Physics 30. That is, if you understand what we just said, and if you remember what we just said, the whole idea of change in potential energy being equal to the work. Let's take a look at this question. It says, moving a small charge from one position to another in an electric field requires 3.2 times 10 to the negative 19 joules of work. Okay, let's circle that and call it W. How much electric potential energy will be gained by the charge? In other words, we're looking for delta E, right? The change in electric potential energy, the potential energy gained. What's the value of delta E? Boy, don't make this harder than it has to be. It's equal to the work, right? Delta E is 3.2 times 10 to the minus 19 joules. This is not a calculation question. This is a definition question. This is another way of asking you to define work in the context of electric potential energy. If you know that work is equal to the change of potential energy, then you've nailed the question. All right? Hey, good news. Just in case you had trouble with this, I've got a couple practice problems for you to work on. I'm going to cover up those answers because I wouldn't want you to see them as you're working on these. I'll give you about 30 seconds to answer both of these questions. Let's see what you can do with them. What's the answer to the first one, guys? Here's the gain in potential energy. What's the work done? Yeah, 1.6 times 10 to the minus 19 joules, right? What about the second one? This one is a little bit harder, okay, but still not crazy hard, I don't think. Okay, we got one position where its potential energy is 6.4, another one where its potential energy is 8.0. What's the work done? Well, the work is equal to the change in potential energy. The change in potential energy is good. 1.6 times 10 to the minus 19. We have to subtract them there, right? Okay. If you know the definition of work and you can do a little bit of subtraction on your calculator, then you should be good for that question. Hey, you ever notice sometimes that we're working on problems and doing a concept, do an example problem, and then we work on practice problems, and you find that, man, I wish we had another practice problem or another example problem because that was a little bit tricky. And then sometimes there's not another example problem. Just in case you're really struggling with this, for whatever reason, they actually gave us another example for this topic in the textbook. Okay, you don't even need to write anything down for this. Let's just go through them real quickly here, okay? When a small positive charge moves from a negative plate to a positive plate, this much work is done. What's the change in potential energy or the gain in potential energy? It's going to be 2.3, right? Work is equal to the change in potential energy. Similarly, for this question, it gains this much potential energy. How much work is done? 4.0 times 10 to the 5 joules, right? Easy enough. Okay, listen, it's easy enough. We laugh at this, right? Because it's so ridiculously easy. It's so ridiculously easy if we know the definition of work, if we know that it's change in energy. This is not an easy question if you don't see the answer in front of you and you don't remember that work is equal to the change in energy. If this is an exam question and you see this and you don't remember that W is equal to delta E, then you're looking at this thinking, I got one piece of data. What do I do with this? I got nothing else. So don't get too overconfident with something like this, okay? It's easy if you remember the definition, okay? But you got to remember that definition. Okay, a couple more terms here. Let's talk about potential energy between parallel plates here now and the movement of these charges between parallel plates. The work done as a charge moves between parallel plates across this electric field. When an electron, or any other particle for that matter, is in between the plates, it experiences a force. Now, the force can be found by using the experiencer equation. Right? F is equal to Q times E, the charge times the electric field. And that force is applied over a certain distance, the displacement of the charge. So, as this charge moves from one plate to the other, it experiences a force, but it also has a displacement. When we multiply F times D together, we get a quantity that we talked about in Physics 20, which is work. So now we're saying work is equal to F times D. We just said it was equal to delta E. Now we're saying it's equal to F times D. It is. It's equal to both. So let's say now that delta E, the change in potential energy, is equal to W, as it was in the last couple problems that we did. But now we can say it's also equal to F times D, the force times the displacement. Sometimes we may need to find the force there by using the equation Q times E. That's my electric field experiencer equation. Sometimes we may be given the force. The displacement and the force must be parallel. Just like in Physics 20 when we were dealing with gravity or any other form of work. They must be parallel to each other. So what do we mean by that? Let's give you an example here. Let's say you got two charged plates. Let's say the top one is negative and the bottom one is positive. And we've got an electron or some negative charge right there. Half a second later, or some fraction of a second later, this charge, for whatever reason, is right here. There is an electric force acting on this charge, and the electric force is this way. If we're given the value of the electric force, great. If we're not, then maybe we can find the electric force using the electric field experiencer equation Q times E. I'm going to label three different displacements, though. Displacement A, because that's where it went, right? Displacement B, in other words, the y component of that displacement. And displacement C, the x component of that displacement. If we wanted to find the work done in moving this charge from this position, position 1, to position 2, we would use the force that we identified right there. What displacement would we use, A, B, or C? What displacement's relevant here, A, B, or C? The diagonal displacement, the vertical, or the horizontal? Parker says it would be B. How many people agree with that? Absolutely. Absolutely, Parker. Good. The horizontal doesn't matter. It's not in the direction of the force. A doesn't matter because it's B and C combined. The only thing that matters here is B. Okay, the only thing that matters is the force and the displacement in the direction of that force, parallel to that force. Does that make sense? Okay, it's not a huge deal. Okay, but if you ever see a question where, hey, look, this charge is going in a couple of different directions like this, all we care about is the direction of the displacement that's in the direction of the force. Another term, electric potential. Hey, let me tell you a quick little story here. On Sunday, my 4-year-old son and I went to a bank in Calgary where they have a coin sorter. You can put all your coins into this sorter. It counts it instantly, like less than a minute. It counts all your coins, gives you a little slip. You take it up to the teller. You give it to the teller. They deposit your money in the bank, or they give you the cash, whichever. We had a lot of change. Okay? I had $346 in change. $346 in change. We dumped it in. Okay, took the slip up to the teller. $346. It was great. It was like $346 of found money. You know how when you look in your winter jacket pocket, your winter coat pocket, in October, you haven't looked at it in 6 months, and all of a sudden there's a $5 bill in there? That's kind of what it felt like. Money that never had before. The total money that the two of us got was $346. Now, if I had been really, really nice, a really, really good dad, I would have split it with him. I didn't. I think I gave him a quarter. But if I had been really nice, I would have split it with him. The total money was $346. Let's assume for a second that I did split it with him. If I split it with him, then the money per person would have been what? $173. So the total money was $346. The money per person was $173. Does that make sense? When we're talking about electric potential energy, we're talking about, using the analogy, the $346. Potential energy is the total. But if we talk about potential, we're talking about the 173, the money per person. Electric potential is the amount of potential energy per charge. Right? The 173 was the money per person. Potential is the energy per charge. The amount of electric potential energy per charge. Now the symbol for potential is V, capital V, not a lowercase v, because a lowercase v would be speed. Capital V is potential. And potential is equal to the potential energy divided by the charge. It would be like saying the potential, when my son and I went to the bank to cash in our change, was equal to the potential energy, $346, divided by the amount of people, the number of people, 2. 346 divided by 2 is 173. It's the amount of energy divided by the amount of charge, just like it was the amount of money divided by the amount of people. Now, what do you think the units for potential would be? Joules per coulomb, good. What do you think an equivalent set of units for joules per coulomb would be for electric potential? Another term for electric potential, by the way, voltage, same thing. What do you think the units for potential would be, or for voltage would be? Well, you guys know this. How about volts? Ever look at a battery? What does it say on the side? 1.5 volts. Sometimes we just abbreviate that with a capital V. Electric potential energy, the energy stored in the system of two charges a certain distance apart. Potential, it's that energy that we just found per coulomb of charge. That energy divided by the charge. What about potential difference? So my son and I came out of the bank with $346. That's the energy. The potential was $173 because that's how much each of us had. Then we go to 7-Eleven and we buy a Slurpee. We each buy a Slurpee. It costs $2 each. Electric potential energy was 346. The potential when we started, when we went into 7-Eleven, was 173. The potential when we come out was 171 because we each spent $2 on the Slurpee. What was the potential difference? What was the difference in the potential? If our potential was 173 and then it was 171 because we each spent $2. What's our potential difference? 2. Now, there's 2 ways that we can figure out what the potential difference was, right? We can say, look, my potential was 173. Now it's 171. The potential difference is 2. Or we can say, the potential energy was 346. Now it's 342 because combined we spent $4. So the change in energy would be 4 divided by the amount of charge, or the 2 people would be 2. Either way we look at it, the potential difference is $2 using the analogy. Electric potential difference, exactly what it says. It's the difference in electric potential between 2 spots. So potential energy, it's the energy stored in the system of 2 charges. Potential is the energy per coulomb. Potential difference is the difference in energy per coulomb. And we could find it by saying delta V, Vf minus Vi, or we can say delta V is equal to delta E over P, or sorry, delta E over Q. One final term that that we want to identify before we work in the problems here. It's called an electron volt. Let me ask a couple questions before I define that, though. What if I asked you to calculate speed? What units would you use to calculate speed? What units would you usually use? Meters per second? Yeah, usually you'd use meters per second. Are there any other units that you could use to measure speed? Like what? Good, kilometers per hour. There's miles per hour. There's even some more obscure units that you could use, like centimeters per second or millimeters per second if you're talking about something really slow, or kilometers per second if you're talking about something really, really fast, right? Usually meters per second works well for us. But sometimes you're dealing with a snail, and meters per second isn't really a practical unit to use because snail's so slow. Sometimes you're talking about a spacecraft where, look, it goes so fast, or even a planet goes so fast, meters per second isn't really a convenient unit to use. Maybe you want to go kilometers per second in that case. So meters per second is the standard unit, but there are other units that we can use to measure speed. What's the standard unit for energy? Joules. It's a standard unit. We can always use that, but sometimes it's not so convenient to use a joule. When we're measuring the electrical energy used in our houses, when your parents get your power bill at the end of every month, it's not measured in joules. That energy is measured in kilowatt hours. It's because we use so many joules that it's just not convenient to measure it in joules. 1 kilowatt hour is 3.6 million joules. 1 kilowatt hour costs about 9 cents. So you use a lot. My power bill at the end of every month is $100. I use a lot of joules. I use a lot of kilowatt hours, right? It's not convenient to measure it in joules. It's just not convenient. It's valid, but it's not convenient because we use so much energy. Sometimes the amount of energy that's used is really, really small. A unit that we can use instead of joules to measure a small amount of energy would be an electron volt. An electron volt is defined as the energy that's gained or lost, depending upon which way the electron goes. It's the energy that's gained or lost by an electron as it goes through a potential difference of 1 volt. Think of it as, hey, you got an object, a mass. It's the amount of energy that's gained or lost by the mass as it goes up or down through the gravitational field. Okay, the amount of energy gained or lost by an electron when it goes across the potential difference of a volt. Now its value, an electron volt has a value that's equal to 1.6 times 10 to the minus 19 joules. Just like I said a minute ago, that a kilowatt hour has a value of 3.6 times 10 to the 6 joules. You don't need to know that, by the way, but so then essentially the conversion factor between electron volts and joules is 1.6 times 10 to the minus 19. It's not a coincidence that it's the same number for as the charge of the electron. If we calculated that, we'd see that in fact it would work out to be that value. Sometimes you're going to have to convert, just like you have to convert from kilometers per hour to meters per second. Sometimes you're going to have to convert from electron volts to joules and vice versa. So how do we do that? First of all, on your data sheet, know where that is. Find that on your data sheet. Because you got to remember that that's the conversion factor. Then, hey, look, if you want to convert 2.3 electron volts to joules, let's say 1 electron volt is 1.6 times 10 to the minus 19. Set it up as a fraction. Is equal to 2.3 electron volts over x. You're solving for the joules. That's equivalent to 2.3 electron volts. Maybe you want to convert 4.8 times 10 to the minus 17 joules to electron volts. Well, then let's say once again, 1 electron volt is 1.6 times 10 to the minus 19 joules, set it up as a fraction, is equal to x electron volts over 4.8 times 10 to the minus 17. Solve for x. Some of you are really good at determining whether you just multiply or divide. Some of you might say, oh, okay, I want to go from electron volts to joules. I just multiply by 1.6 times 10 to the minus 19. I'm not good at that. That's what you do, by the way. You do multiply. But in the end, I'm not good at that. I forget all the time. Do I multiply or do I divide? Okay, it works better for me if I set up a ratio like this, because I can't go wrong. As long as I can rearrange equations, then I can't go wrong. All right? Okay, let's do an example here, 565. Moving a small charge of 1.6 times 10 to the minus 19 coulombs. That's Q, right? That's the charge. Between two parallel plates increases its electric potential energy by this value. So in other words, this is going to be delta E, the change in electric potential energy, the gain in electric potential energy. We're going to find the potential difference. Well, we know the potential difference is VF minus VI, but we don't know what VI and VF are, so that's not going to be helpful. We also know it's equal to delta E over Q. Let's say 3.2 times 10 to the minus 16 divided by 1.6 times 10 to the minus 19. That works out to be 2 times 10 to the 3. It shouldn't be joules on the bottom, it should be coulombs, right? 2.0 times 10 to the 3. What are the units? Joules per coulomb, or 2.0 times 10 to the 3 volts, right? Okay. So what have we seen today? Electric potential energy, electric potential difference, electric potential energy difference, which is the same thing as work. Lots of terms that sound almost the same. Lots of terms that are almost the same, but lots of terms that have subtle differences between them. So if we can keep straight the subtle differences there, we should be fine. Not crazy hard stuff. Just got to keep straight those subtle differences between all those terms. Okay, let's take a look at the practice problems that go with this in 565.